Okay, this is the 2022 AS Chemistry AQA Paper 1 walkthrough. Let's get to the marks. Let's go. Question 1. This question is about ionization energies of group 2 elements. Explain why the first ionization energy of the group 2 elements decreases down the group. All right, let's check this out. So if we look at atoms, what happens to them as you go down the group? Yes, they've got nuclear charge in their nucleus, and then they have shells around the outside. But as we go down a group, down the periods, remember, within a group, you're increasing the number of shells. So if we go from period 1 to period 2, or period 2 to period 3, we're increasing the number of shells. So why does the first ionization energy decrease? Essentially, the first point is atoms, get larger. So, or you can say atomic radius increases. Now I'm going to use a little upwards arrow for increase, something you can do in your notes as long as you don't write it in your actual exams. What does this mean? This means that the electrons are further away from the nucleus. Now, I use E- as my symbol for electrons when doing notes, just to save some time. So electrons further from nucleus. What else do we want to say? Well, also, look at the number of rings in my crusty little diagram. The number of shells, or number of shells, is also increasing. Or you could say more shielding as we go down the group. So there's an increasing number of shells and more shielding. And this, combined with the increased distance of the outer electrons from the nucleus, means that there is a weaker attraction between outer electron and nucleus. Booyaka. There you go. That's going to cover all your points, more damn. Now, I would say the most common error here is when people come out and say something like, well, definitely don't say this. Don't say nuclear charge gets weaker down the group. It certainly doesn't. So that would be a big no-no. Nuclear charge does not get weaker down the group, it gets stronger. But despite the increase in nuclear charge, which should hold those electrons more easily or more strongly, we get an increase in shielding, so that nuclear charge is kind of blocked by those shells of electrons. The outer electrons aren't feeling it as much, and also those outer electrons are further from the nucleus. So make sure you say weaker attraction. You can say weaker electrostatic force of attraction if you want to be super technical, but there we go. Awesome. Let's move on. Give an equation including state symbols to represent the process that occurs when the third ionization energy of magnesium is measured. Okay, so this is writing your equations. Let me show you the incorrect one first. So this will be the typical mistake that people would make. They would put like, okay, they would go like Mg 3 plus, or sorry, they would go Mg goes to Mg 3 plus 3 electrons. What's the problem here is that the third ionization energy, we're already dealing with a Mg2 plus ion. You have to remove one electron at a time. So we're starting with an Mg2 plus ion like this. And we are going to an Mg3 plus ion. And instead of plus 3 electrons, well, we're just removing one extra electron to go from 2 plus to 3 plus. So a lot of people will put 3 electrons there, and that will be their big screw up. So watch out for that. And of course, what state, when we do ionization energies and we measure them, what state are the ions in, or the atoms or ions? They're all vaporized. So we have to put our gaseous state symbol next to the ions. And there you go. That's your correct answer. And of course, we do have an incorrect answer here. And we got our correct answer here. So make sure you're writing that one. That is the correct equation for the ionization energy. Right. Explain why, let's zing. Explain why the third ionization energy of magnesium is much higher than the second ionization energy of magnesium. So why, when we go from 2 plus to 3 plus, does it require a lot more energy than going from, say, 1 plus to 2 plus? Well, let's check out. For that, we need to check out the electronic configuration of magnesium. Magnesium has, we're not interested in the mass number, of course. We're interested in the atomic number, which also tells us the amount of electrons in a neutral atom. So magnesium has the structure 1s2, 2s2, and 2p6. Okay, that's 10 electrons. I've got two more. What's the next one? The third energy level, got 3s2. So when we go to the magnesium 2 plus ion, we will have already removed these two electrons. So we've actually taken those two away. That shell has disappeared. We're now breaking into a new energy level and a new subshell, the 2p subshell. So the main reason is we're breaking into, or let's not say breaking in, sounds like we're robbing a house. We're removing an electron from the two, we can say from a new energy level and 2p, 2p subshell instead of 3s subshell. Now, why is that important? Well, it's closer to the nucleus, so 2p is closer to nucleus and less shielded. I can't spell shielded. Shielded. There we go. Okay, so the key things here are that it's closer to the nucleus, the 2p subshell, so it's suffering less shielding, whereas the 3s electrons were shielded by the 2p electrons, so they were easier to remove. Also, we're cracking into a whole new energy level, which is a lot closer to the nucleus, so it's going to feel a stronger attraction, hence the higher ionization energy as you go through the subshells. All right, guys, that's that question done. Let's move on. Here we go, go. Question 2. This question is about acid and base titrations. Citric acid reacts with sodium hydroxide. That's an alkali. So we can see which one is the sodium hydroxide. So we're going to be interested in this question in the citric acid. Now, my eyes are terrible, but I believe that's C6. So let's just make that a bit larger. C6H8. We're going to need its molecular formula later on in this question. So right, so that's the citric acid, that's the sodium hydroxide. Here we've got a reaction. A student makes a solution of citric acid by dissolving some solid citric acid in water. Okay, describe a method to make an accurately known mass of solid to a beaker to make a solution. Okay, God, I read that like a right troubled person. So if you want to make sure you add a known mass of solid to a beaker, so here's my beaker, and if I want to add a known mass of solid, obviously we're going to need to weigh it. Now, there's two options here. You can take your weighing vessel. This could be called a weighing boat or a watch glass, or I could just use a beaker here, whatever that is, and I could zero the scale. Now I can add my mass in, and that is the mass of the total thing. So that will just record the mass of the solid because we've wiped out the mass of the beaker, the weighing boat, or the vessel which we're using to weigh the solid. So we'll know the mass of the solid, and then we can tip it in to here. And we'll know when we put the beaker back, a number will come up because not all of your solid is going to leave your weighing vessel, your beaker or your watch boat, whatever, your weighing boat. Not all of your solid is going to leave it. So you put it back and you have to subtract whatever's left over. So simple as that, really. Or you can just say weigh the beaker beforehand. So we can just say weigh, or let's be a little bit more technical, measure the mass of the weighing boat before. Okay. I would just add in, make sure you zero the scale first. So you just good practice to make sure it's on zero. Measure the mass of the weighing boat before. Then after adding solid, empty solid into beaker, reweigh mass, and subtract. Okay, so essentially you want to find out if there's any solid left in the beaker. So you put it back on and you'll be able to see if there's any solid left back on. Okay, let's move on. I'm sure that was explained very badly, but that's probably the easiest question in the paper. The student dissolves 0.34 grams of citric acid in water and makes the solution up to 500 centimeters cubed. Calculate the concentration in mole dm to the -3 of citric acid. So all we've got to do is convert these grams into moles and then convert these centimeters into dm. And what does this mean? This means we've got to divide moles by dm. So first let's get the moles, then the dm, then let's divide them. And there's your answer. So hopefully you can all remember your triangle from GCSE. You got mass over mr times moles. So we're going to write down the mass of the citric acid, 0.834 grams. We're going to divide that by 192. I believe that's the MR. And then we're going to, no, what am I timesing 100 for? I've had a moment. Deleted too much. So we're going to divide that by that. Let's just zing that up. You might say, how did I get the 192? Basically, we've got to do 6 times, oh gosh, calculator on. 6 times 12 plus 8, because 8 times 1, plus 16 times 7, and that will equal 192. So that is the MR of the citric acid I've written in green up there. So you just add this all up, you find the MR of that, and that will give us our moles. So 0.834 divided by 192 equals 4.34 times 10 to the -3. Now, that's supposed to be a 4 there, not a 1. Never mind. So we now have our moles, okay? Let's find out our dm. What do you think 500 centimeters is divided by 1,000? Super easy calculation. So just looking at 0.5, aren't we? So divide that by 1,000, put into decimeters, and we've got 0.5 dm cubed. We're now going to go moles over dm, so N over V equals C, and that's our concentration. So divide that by 0.5, and we get 8.6875 times 10 to the -3. Boom. Now, we might want to round this up. So if I round this up, what would you round that to? Let's round it to boom. All over the place here. It's going to get messy. 8.69 times 10 to the -3. Great stuff. All right, guys. So that's my final rounded answer there. And on here, the student uses this method to complete a titration. They rinse the burette with distilled water. They fill the burette with sodium hydroxide solution. Use a measuring cylinder to transfer 25 centimeters of citric acid solution into a conical flask. Add 5 centimeter cubed of indicator. Slowly add the sodium hydroxide solution from the burette into the conical flask. Add the sodium hydroxide solution dropwise near the endpoint until the indicator just changes color. Repeat the titration to get concordant results. The method used by the student includes 3 practical steps that will lead to an inaccurate final result. So we've got 3 practical steps that are inaccurate. For each of these steps, identify the mistake and explain why it's a mistake and how it can be overcome. Let's go, peoples. So first thing I want to do is just go down from the top and check each sentence and see if there's a mistake. So rinse the burette with distilled water.
there's a problem. What's the problem with rinsing a burette with distilled water? So this is a mistake. We're identifying it, and the identification of the mistake is rinse burette with distilled water. Now, what they should have done, why is that a problem? That's going to decrease the concentration of the alkali. The alkali in question here is sodium hydroxide solution. And this is probably going to be our known concentration. You don't want to decrease the concentration of that. It's going to mess all your calculations up. So what is the solution to this? How can it be overcome? Right. They should have rinsed with the same sodium, whoopsie, hydroxide solution. And what I mean by that, the same concentration of sodium hydroxide solution. So is what they should have rinsed it with. Right, let's check for any more mistakes. Let's go back and just check down. Here we go. Fill the burette with sodium hydroxide solution. Okay, that's all right. Filling the burette with sodium hydroxide solution. Should use a funnel, but no need to get picky. Use a measuring cylinder to transfer 25 centimeter cubed of the citric acid solution to the conical flask. Right, what should they have used instead of a measuring cylinder? So, used a measuring cylinder. Now, that's not the most inaccurate way to measure out a volume, but it's not the best. It's not the most accurate. It's not too inaccurate, but it's not that great. So use the measuring cylinder, which has a high level of uncertainty. There's a high error in the results here. Remember, you've got the meniscus, the little bit which bubbles, and it's difficult to read. And there's going to be a higher level of error and uncertainty in the use of a measuring cylinder. So they should have used, what they should have used is a volumetric pipette. You can probably just say use a pipette, but the volumetric means the one that measures a volume, not the dropping pipette that you use for food tests and staining and things like that. Okay. What's the next mistake? Let's go back up and get the old highlighter pen out. Let's highlight in a slightly different color. Okay, whoa, just below that, add 5 centimeter cubed of indicator. Okay, that's an issue. Add 5 centimeter cubed of indicator is the mistake. This would mask the endpoint or make it difficult to tell when you're at the endpoint. How are they going to solve this? They should have used a few drops. I don't know, something like 2 to 5 drops, something like that. That would have been fine of their chosen indicator, methyl, orange, or phenolphthalein. You don't want to use so much indicator. I mean, 5 centimeters is like 40 drops or something. Okay, let's check. Let's get a different highlighter out, please. Thank you, Bob. We will go with green. We haven't added green yet. So slowly add the sodium hydroxide solution from the burette into the conical flask. Nothing wrong with that. Add the sodium hydroxide solution dropwise near the endpoint. That's correct. Until the indicator just changes color. Okay, you could, if you were eagle-eyed, have a problem with this. Basically, they want you to stop as soon as the indicator changes color. Okay. Stop when indicator just changes color. That is a potential error there. They should be, as soon as it changes color, they should swirl the flask to ensure that all the reactants have reacted. Sometimes you get a color change, and if you wait 10 seconds, that color disappears because it hasn't fully reacted. You're getting close to the endpoint. You'll get a color change, but it will go colorless again after. You need to swirl the flask to make sure you've definitely reached the endpoint. So stop when indicator just changes color. What should they have done? They should, what we want to say is, why is that a problem? So we want to say the reaction may not be complete. Endpoint might not have been reached, they should swirl the conical flask. And that is the end of that question. Let's move on. Where am I going to put this bit? This bit is over here. So you don't need all of these. You just needed, you sort of get 2 marks for each of these paragraphs, which identify the mistake, say the problem with it, and what's the solution. They should really, in that final one, they should really swirl the conical flask and ensure that the color change is constant. Okay, guys, let's move on. Okay, 2.4. Table 1 shows the student's burette readings after the mistakes in the practical procedure have been corrected. Final reading, start reading, titra. So this is a rough titration. Remember, this will not be included ever in the calculations. But then we have run 1, run 2, run 3. 22.95, 00, 46, 22.95, 26.3, 3.4. Complete table 1, use the data in the table to calculate the mean. So what we need to do is literally just take 22.95 and take away 0. So final reading minus the start reading. So the first one is 22.95. Then we have I need to bust out my calculator. $23.10. And then we have 26.30, subtract 3.40, we have 22.90. Now what we need to do is work out which are the concordant results. So the concordant results have to be the 2 results that are closest together or within 0.1 of each other. And we can see that 22.95 and 22.90 are both within 0.1 of each other. So we're going to use those as our concordant results. So 22.95 plus 22.90, divide those both by 2. We're going to get 22.925. Now you could round that up if you prefer to 22.93 centimeter cubed. So it's up to you which one you want as your mean titra. Both are correct, but some people prefer to round up to 93 as all the results are to 2 decimal places. So let's look at the next question. 2.5. The total uncertainty in the use of the burette is plus or minus 0.15. Calculate the percentage uncertainty in run 1. So run 1 is over here. And for those of you that haven't memorized this yet, you need to memorize it. So it is like this. Percentage uncertainty is equal to the uncertainty divided by the measurement. So divided by your measurement. So we're just going to do that one here. And it's going to look something like this. So they've been nice to us here. They've given us the total uncertainty as 0.15. We haven't had to calculate that. Sometimes that can be a pain. So now we're going to multiply this by 100. 0.15 over 22.95 times 100. And that's going to give us 0.65%. And that's the percentage uncertainty in this situation. Sometimes you have to calculate the uncertainty by combining the uncertainty of 2 different measurements. Anyway, we didn't have to do that this time. So let's move on. Okay, this is question 3. This question is about the shapes of molecules. Complete the table 2 by drawing the shapes of both ASF5, couldn't read that, and KRF2. So complete these molecules showing all lone pairs of electrons that influence the shape. Deduce the bond angle in ASF5. Okay, so we don't have to do it for KRF2. Here's a little table for us to draw our pictures in. Let's get to it. So let's go. So first off, Let's look at this. AS is in group 5 of the periodic table. That's arsenic. So it's in group 5. It has 5 outer electrons. Now you can see here with F5, that means it's got 5 bonds. So we take the 5 outer electrons around the central atom, we plus it to the 5 bonds, we divide that by 2 and find that ASF5 has 5 electron pairs. My P here stands for pairs. I then take the 5 pairs, I subtract the 5 bonds, and that tells me there are 0 lone pairs that influence the shape. And so what we have here is going to be well, that would help if I didn't put a fluorine atom in the middle. That's not the central atom. So the central atom, of course, is arsenic here, which has the symbol AS. And then what we do here is attach our 5 bonds. And they arrange themselves. When you have 5 bonded pairs of electrons around the central atom and no lone pairs, we get this shape. The dashed line means going into the paper, and the solid black line is coming out of the paper. And this is known as bipyramidal. It doesn't ask us for the name, but it's called bipyramidal if you wanted to know. And the bond angles are 90 and 100, oops, not 200, thank you, 120 degrees. So there are bond angles. So that's going to score us 2 marks for that. Now, the next one is a highly unusual one that is not covered in most of the textbooks and stuff, but just follow the pattern or the strategy to give yourself the best chance possible. So krypton, Kr, is in group 8. So we say there's 8 electrons around the central atom, and it's bonded to 2 fluorine molecules. So there are 2 bonds. If we do 8 plus 2, divide that by 2, we find there are 5 pairs of electrons again. This time, however, there's 5 pairs of electrons, but we subtract the 2 bonded pairs out of the 5 pairs, we find there's a total of 3 lone pairs. This is highly unusual. We don't normally deal in situations with 3 lone pairs in A-level chemistry. So this one is a little bit of kind of applying your knowledge. So now we know that. We know there's going to be 5 pairs of electrons around it, 2 are bonded and 3 are lone. So we can kind of guess at the shape here. I'm going to give myself 2 Bugs Bunny ear lone pairs there. We're going to go with a fluorine atom here, a fluorine atom here, and then 1 more lone pair down here. I mean, it doesn't matter if I put the 1 lone pair below and the 2 above, or the 2 below and the 1 above. That's it. And that will get you your 3rd mark. So congratulations. Let's move on. Final time. Guys, question 4. This question is about intermolecular forces. Complete the diagram to show how 1 molecule of ammonia can form a hydrogen bond with 1 molecule of ethanol. Include all the lone pairs of electrons and partial charges on the atoms involved in the hydrogen bond. Right, there's 2 ways we can do this to get the full marks. So I'm going to show you the first way. First way is to say, well, which of these, oxygen or hydrogen, is going to be bonded to the ammonia? Well, either one can be bonded to the ammonia. So I'll start with the version where oxygen is bonded to the ammonia. Now, there are 2 lone pairs on oxygen, and I've then got a dash, that is the worst hydrogen dashed line, to a hydrogen atom. Now, the hydrogen atom is electropositive compared to the oxygen, which is electronegative. So there's my partial charges. And then that's going to be attached to an ammonia molecule. Now, I don't need to show the lone pair on the ammonia, on the nitrogen here, because it's not involved in my hydrogen bond. It's the lone pair of electrons on the oxygen, which are bonded to the partially positively charged hydrogen. So let me show the other option. Okay, that's option number 1. Let's rub this out and show you option number 2. So very similar, because we're involving the same molecules. But now we're saying, what if this hydrogen atom here, which is electropositive, forms that's a much better hydrogen bond dashed line with the negatively charged nitrogen atom in the ammonia molecule. And of course, that is going to have the negative partial charge. And so this is the other version. Of course, these hydrogen atoms are electropositive as well and can bond to another ethanol molecule. But the question specifically says it wants all the lone pairs of electrons and partial charges on the atoms involved in the hydrogen bond. And they're only asking us to draw one hydrogen bond. So I just need my lone pairs and partial charges. And I've drawn the dashed line for the hydrogen bond, so that will get me 3 marks. Boom. Right, let's move on. We've got a little table here of electronegativity. Hydrogen scores 2.1 on the Pauling scale, carbon 2.5, nitrogen 3, oxygen 3.5, and bromine 2.8. Define the term or electronegativity. Now, that's the ability to draw electrons in a covalent bond, or that's the ability to draw, let's say, to attract electrons in a covalent bond. I reckon my brain is slipping here, but I reckon the withdrawing ability of the ability to withdraw electrons in a covalent bond. Essentially, what happens is if you're more electronegative, so say for example, we had hydrogen attached to bromine, what that would mean is the 2 electrons that are in the bond would be closer to the bromine than they are to the hydrogen. You see there, I've drawn them closer to the bromine. The bromine is withdrawing the electrons in that covalent bond. And that leads us to down below, deduce the 2 atoms that will form the most polar bond. Which 2 will there be a bigger difference? And so we'll get a more polar bond. And all you've got to do here is look at the difference. So if I look at H and O, the biggest difference is between these 2, and it's a difference of 1.4. Whereas, say you looked at carbon and nitrogen, they're not really going to form a polar bond because there's only a difference of 0.5. Okay, so what we're going to do here, the 2 atoms that form the most polar bond are going to be O and H. Now, you don't have to draw a line between them, but there we go. I have. So O and H, yeah. And remember, there are 3 types of hydrogen bonds. You've got one when you have O and H formed. So if you've got O and H bonded like that, that molecule will be able to do hydrogen bonding. Or if you have N and H or F and H, you will get hydrogen bonding. Right, let's move on. Moving on. Okay, so moving on, let's explain here 4.4, the CBr bond is polar. Explain why CBr4 is not a polar molecule. So what they're saying here, we have a little conundrum here. We have the CBr is actually polar, and what that means is that those electrons are going to be drawn towards the bromine, making that partially delta negative and this delta positive. They're the worst delta negative and positive symbols you could ever see, but there we go. You get the issue. Right. The problem is because carbon has 4 electrons in the outer shell and it's forming 4 bonds, it's going to take a tetrahedral structure. And what that means, let's not do a partial charge there, Tom. What that means is that the bonds are going to be all the same angle away from each other, which is 109.5, and they're going to form the tetrahedral shape. And because of that, got to draw a wedge. That is a bad wedge, but because of that, they're 109.5 degree bond angle between each of these. So each bond is the exact same distance from each other and all the charges cancel out. The electron distribution is even, or electron charge density is evenly distributed in this molecule. So we can say tetrahedral shape. It is a symmetrical molecule. The dipoles cancel each other out, and that will get you all your marks. So that's what you want to say there. They'll still be delta negative and delta positive. Not going to bother drawing it on because I'm taking far too long as it is. But those charges will cancel out essentially, and the whole molecule will not be classed as a polar molecule. Right, 4.5, suggest in terms of the intermolecular forces for each compound why CBr4 has a higher boiling point than CHBr3. Now, this can be a little bit unusual because CH, okay, Br3, so it's going to be tetrahedral as well. Yeah, whatever. So CHBr3 is also tetrahedral. However, because it's not symmetrical, it's going to be a polar molecule. So this, yeah, I'm waffling here. CHBr3 has both van der Waals forces. You'll need to write that out. So it has van der Waals forces and induced dipole forces. So it's got both van der Waals and induced dipole forces. However, as it is a smaller molecule, smaller you say, isn't it the same size? Well, no, bromine's atomic mass is far greater, many, many, many times greater than a hydrogen. So it's the CBr4 is a lot bigger. So, however, it is a smaller molecule than CBr4, which has more electrons and so much stronger, or more, we can say instead of stronger, has many more van der Waals forces. And the strength, the increase in the van der Waals forces in the CBr4 is enough to overcome the fact that CHBr3 has both van der Waals and dipole-dipole. So if they were of a similar mass, these two molecules, then the one with the extra intermolecular force, the dipole-dipole, the induced dipole-dipole, and the van der Waals would have the higher boiling point. However, as it is far smaller, yeah, it's got weaker van der Waals forces. And so that is our reason. Okay, thanks, guys. Okay, question 5. A sample of antimony is analyzed on a time-of-flight mass spectrometer and is found to contain two isotopes. We have 121 SB, sounds like tin, maybe. Oh, not tin, it's antimony. A sample of antimony is analyzed in a time-of-flight mass spectrometer and found to contain two isotopes, 121 SB and 123 SB. Okay, so just for visual purposes, we have two isotopes. Oh, wrote that the wrong way around. Never mind. And 123. Whoopsie. Okay, so there are two isotopes we've been informed about. After electron impact ionization, all of the ions are accelerated to the same kinetic energy and then travel. That sounds like that's going to be important, the same kinetic energy. So, as you know, during all time-of-flight spectrometry, they end up with the same kinetic energy and then travel through a flight tube that is 1.05 meters long. A 121 Sb plus ion takes 5.93 times 10 to the minus 4 seconds to travel through the flight tube. Then the kinetic energy of an ion is given by the equation Ke equals half mv squared, where kinetic energy is measured in joules, mass in kilograms, and speed in meters per second. Calculate the mass in kg of 1s1 Sb plus ion. Calculate the time taken for a 123 Sb plus ion to travel through the same flight tube. Using Avogadro's constant, L equals 6.022 times 10 to the 23. So we've got two parts to this question, which makes this one slightly different from the norm. So the first step is to calculate the mass in kg of an 1s1 Sb plus ion. Well, of course, that number I keep saying 1s1 or 121 or 123, 1s, don't know what I'm on about there. That mass number, of course, is the mass of a mole. So what we need to do is say, okay, if we know that that is the grams in 1 mole of 121, then of that ion, then we need to divide by 1,000 to convert that into kg. And if we do that, we get 0.121 kg. Now that is per mole, okay? We don't want it per mole because the mass number obviously is per mole. We want it in the form of 1 ion, as it says over here. So we then need to divide that by Avogadro's constant. to find out exactly the mass. So I'm going to put divide by L, bearing in mind that L is 6.022 times 10 to the 23. So let's find out what that is. Okay, so we're going to go 0.121 divided by 6.022 times 10 to the 23. We get an answer of 2.009 times 10 to the minus 25. There's a whole bunch of other numbers, but they're pretty low. So the next step is, so that's our first step covered. And that is the mass in kg of one ion. So that's the mass in kilograms of an ion. And that covers basically covers this step. We've done that. Brilliant. So we're going to definitely pick up a mark, perhaps 2 of the 5 marks there. So let's go. The next step to this question, he says, geez. Calculate the time for a 123 SB plus ion to travel through the same flight tube. So, bearing in mind they're going to have the same kinetic energy, we can only do this if we work out the kinetic energy of this first ion. Then we'll know the kinetic energy of the second ion and be able to calculate the speed of it or the time it takes to travel through the tube. So let's first of all work out the kinetic energy of this first ion. So in order to do that, we need to find the velocity of that first ion as well. So, and to find the velocity of the first ion, we are going to have to do, velocity, or let's go over here. Velocity is equal to distance over time. And guess what? They've given us the distance. The distance was 1.05 meters long and the time was 5.93 times 10 to the minus 4 seconds. So let's find that out. So let's go 105 meters and let's divide that by 5.93 times 10 to the minus 4 seconds. And what we get then, we get 1.05 divided by 5.93 times 10 to the minus 4. We get a velocity of 1770.657673, and that's meters per second. So that's our velocity of the 121 ion. Now, what I can do is find the kinetic energy out of that ion by then putting that velocity and rearranging this kinetic energy equation. Actually, I don't need to rearrange it, do I? So let's do it. Ke is equal to half our mass times our velocity. So half 2.009 times 10 to the minus 25. And I'm going to want to multiply that by our brackets, our velocity squared. This has not worked out well. Get rid of that shit. Half times 2.009 times 10 to the minus 25. And we're going to multiply that by the velocity squared. So 1770.65 7673, close bracket, and we're going to put that little arrow up, meaning squared. And what do we get when we do that? Let's check it out. So let's square answer. Okay. And then multiplied by 0.5 times 2.009 times 10 to the minus 25, close bracket, equals, we get 3.149 or 3.15. So we get a kinetic energy of 3.149 times 10 to the minus 19. We could just call that 3.15, more or less. So there we go. That is our KE. Now we know that the KE is the same for V. Whoa. It's also the same for, yeah, that's also the KE of SB123. Okay, so that's the same. That's the KE for the 123 SB plus ion. So let's stick that in there. The aim of this next part of the question is calculate how long it takes for that ion to travel down the same flight tube. We need to find the velocity. Now, all the ions have a different velocity, and we would expect this ion here, as it's heavier, to have a different velocity. So we're going to need to find the mass of that out, rearrange the KE question to find its velocity. So V123 is going to be equal to 2 times the KE, so we want to get rid of the half, and over the mass, and we want to square root that, and that will give us the velocity. What is the mass of 123? So the mass of this ion here is going to be 0. Remember, we had to divide by 1,000 to put it into kilograms. So it's going to be 0.123 over Avogadro's. That's equal to the mass. So let's do that now. 123 divided by 6.022 times 10 to the 23. We now know that one ion is 2.04 times 10 to the minus 25. So it's a little bit heavier than our 121 ion. Remember, the 121 ion, which is obviously lighter, one particle weighed 2.009 times 10 to the minus 25. This is 2.04 times 10 to the minus 25. So it's just that little bit heavier. And we want to divide the mass by 2 times the kinetic energy. So we're going to do 2 times 3.149 times 10 to the minus 25. Sorry, minus 19. Oh. So let's do that. 2 times 3.14 times 10 to the minus 25 equals, whoops, just said that wrong and did it wrong. 2 times 3.149 times 10 to the minus 19. And we get that is double the kinetic energy. And now we want to divide it by the mass, which was 2.04 times 10 to the minus 25. We get that. Now we need to square root the answer. And if we square root the answer, this is what we get. Where is my pen? So we're going to square root. And our velocity is going to be just a little bit slower. And you'd expect that because it's heavier. Look, it's 1757.058 594, and that's meters per second. Okay. What do we need to do next? Well, we needed to calculate the time. So now we have the velocity, that's V123. We can stick that in the, we're gonna have to go all the way up here. We can rearrange distance over time and velocity to find the time. So we're gonna do D over V equals T. And that's gonna be 1.05. And we're gonna divide that by our velocity, which is 1757. And let's see what we get. So we get a time of 5.9, and this is the answer here, which I'm running out of room here. This is the answer for the time. And the answer to that is 5.975 times 10 to the minus 4. So we can see if we compare the times as we would expect, this time of 5.975 times 10 to the minus 4, it's a little bit slower than this 5.93 times 10 to the minus 4 that the other ion took. So it's just that touch slower. And of course, we'd expect it to be slower because it's heavier and it's going at a smaller velocity. And we also calculated its velocity, which was not as fast. This one was traveling, the 121 ion was traveling at 1,770, and this one was traveling at 1,757. So you can see there the difference in velocity and therefore the difference in the time it took to travel down the same length of tube. All right, guys, that will secure you all of your marks for this question. Question 6. Iodide ions can be oxidized to iodine using oxidizing agents such as iodate 5 ions and concentrated sulfuric acid. State in terms of electrons the meaning of the term oxidizing agent. So an oxidizing agent is itself reduced but causes another chemical to lose electrons and be oxidized. So an oxidizing agent gains electrons. So a substance that gains electrons would be a better answer, but I'm kind of conscious of time. Let's look at 6.2. In acidic solution, iodate ions oxidize iodide ions to iodine. So we have the IO3 minus iodate ion plus 5I minus plus 6H plus goes to 3I2 plus 3H2O. Give a half equation for the oxidation of iodide ions to iodine. Deduce the half equation to show the reduction process in this reaction. So let's start with the oxidation half equation. Now it says show that iodide ions go to iodine. If we look at our iodide ions, well, we know they're being oxidized because, of course, iodine is -1, its oxidation state, and an element in the elemental form has an oxidation state of 0. So we can see there that it has lost electrons. In fact, it's lost 1 electron. And that's just to show there that what's happening. We need to basically write an equation for this. So nice and easy. We just start with I minus, and then we draw an arrow. Give a little space in case you've got to add things afterwards, and then write I. Of course, iodine is a halogen from group 7, and they are diatomic. So I need to put a little 2 there, and it will release an electron. The fact that it's diatomic means I need to balance it by putting a big 2 here. But the moment I put a big 2 over here to say there's 2 iodine ions, that means there's 2 of these minuses. So there's 2 electrons as well. And that's nicely balanced. So that's an oxidation half equation. The iodide ions are losing their electron to become iodine. Now let's look at the harder half equation, which is the reduction half equation. So when we look at this reduction half equation, we're focusing on the iodate ions. Now, something that we need to note is that it tells us here that the name is iodate 5 ions. That symbol in brackets, that Roman numeral 5, that tells us that the I in the iodate ions is +5 or has a +5 oxidation state. Of course, oxygen has a -2 state, but there's 3 of them. So we've essentially got +5 and -6, which gives us overall that minus charge that we see there on the iodate ion. So that's just to let you know that. Oh, what happened there? That all got a bit funky. Right. What we want to do next, let's just change the color. What's happening to this iodate ion? Well, it's going from +5, and again, the iodine within it goes back to its elemental form, so goes to 0. So it's actually gaining electrons. And just to point that out there for you, in case you hadn't noticed, that is going to be reduction. Why it's gaining electrons, essentially. Okay, so it's going from +5 and it's gaining electrons and it's going to a 0 oxidation state. Anyway, let's get down to the half equation. So this is the reduction half equation, and we're going to start by writing out the iodate ion here. And I want to put my arrow in the middle somewhere, and as I did above, give it some space in case you've got to add stuff. Now, we know that that is turning to iodine. Like so. However, look, we've got oxygen. What am I going to do with the oxygen? Well, what I'm going to do is I'm going to form some water. There we go. H2O. The oxygen's going to form water. And why is that? Do you remember that this was acidified with concentrated sulfuric acid up here? So there's quite a few hydrogen ions knocking about in this equation. Remember, it said here, in acid solution. They're not writing that just for the sake of it. They're letting you know there's hydrogen ions knocking about. And that helps because we can add some hydrogen ions. And why do we need to add hydrogen ions? Well, I've put water on the right-hand side, so I'm always going to need to put some hydrogen ions on the left-hand side to balance that up. Now, of course, we get to the whole balancing issue. Well, I've got I2 over here. You can see I've got two iodine atoms in an iodine molecule, and that's the case. I need to put a 2 here in front of the iodate ions. And I would need to do that to balance it up. And what does that do to the number of oxygens that I have here? Well, 2 times 3 oxygen means I've got 6 oxygens here. So I'm going to need 6 water molecules. And once I have 6 water molecules, I'm going to need to have 12 hydrogen ions. So I just got my daughter next door whistling on a whistle, which is a little bit annoying, but there we go. So I now need 12 hydrogen ions. Now, the problem we've got over here is I need to balance the electrical charge over here. So let's get that balanced up and let's add in 10 electrons. 10 times E minus. Okay, that is the worst looking equation in the world. Let's restart that. 6.3, when iodide ions are oxidized using concentrated sulfuric acid, sulfur dioxide, a yellow solid, and a foul-smelling gas are all formed. Give an equation to show the reaction between iodide ions and concentrated sulfuric acid to form the yellow solid, and identify the foul-smelling gas. Right, so I'm going to need 3 lots of this. Okay, let me talk you through this equation. So we've got 6 iodide ions, and we've got the sulfuric acid. So this forms sulfur from here, the sulfuric acid, and we form iodine from the iodide ions. Now, the oxygen goes on to form water, and therefore we know we need four waters because we've got 4 oxygens in the sulfate group, which means that we're going to need a total of 8 hydrogen ions over here, but 2 of them came from the sulfuric acid, so we need an extra 6 to balance our hydrogen. And there we go. Now we identify the foul-smelling gas, and that is hydrogen sulfide, formula H2S. Or you could just say hydrogen sulfide. And let's have a look at the questions. 7.1, explain how figure 1 shows the forward reaction in this equilibrium is exothermic. Well, it's pretty easy to see here. We get a lower yield at a higher temperature. So lower yield at the higher temperature, and that was the 600 Kelvin. So we get that lower yield at higher temperature. And this tells us the equilibrium has moved to the left. Some people like to say backwards. State whether the forward reaction in this equilibrium results in an increase, decrease, or no change in the amount of gas molecules. Well, we know the forward reaction results in an increase in the amount of gas molecules. How do we know there's more gas molecules on the right-hand side of this equation in the forward reaction? Because when the pressure is low, we get a higher yield. And higher yield always means you're moving to the right. And when the pressure is low, what does the equilibrium or Le Chatelier's principle say? It says it's going to move towards the side with the highest gas molecules. Explain why using a catalyst has no effect on the percentage yield. Well, that's because it increases the rate of the forward and backwards reaction by the same amount. Of course, using a catalyst does increase the speed of which you reach equilibrium, but it doesn't shift the equilibrium. Hydrogen and nitrogen react to form ammonia. We've got the Haber process here. So 3 hydrogen molecules and 1 nitrogen molecule make 2 ammonia molecules. At 74K, the Kc is 0.118. 74K, we've got a volume of 0.150 decimeters, and the equilibrium mixture contains 0.0285 moles of hydrogen and 0.0870 moles of nitrogen. Calculate the moles of ammonia present in the equilibrium mixture. So what we've got to appreciate here, which is important, is the Kc is equal to the products over the reactants. And our products in this reaction is the ammonia. And the square brackets stand for the concentration of those products. And the number outside the brackets, like we're squaring the ammonia there because the coefficient is 2 in the equation. And that is over the hydrogen, which is one of the reactants. And its coefficient is 3. So we're going to cube it. And that is nitrogen. There is no coefficient next to it. It's just 1 nitrogen molecule. So we leave it like that. And the Kc is equal to that. This means if I want to find the concentration of ammonia or NH2, I've got to do Kc times H2 cubed times N2. So if I do that, I'm going to do 0.118, and I'm going to multiply that by, oh gosh, 0.0285 cubed, whatever, divided by 0.150. Yeah, I could have done that separately, times 0.0870. Oh my days. And what we're going to find is that NH, that is the most ugly thing ever. NH squared, when we pump that all into the calculator, we find that NH squared is 4.69 times 10 to the minus 4. Now we want to square root that. And if we square root the NH2 like that, we're going to get rid of that. And we are going to find the concentration is 0.0217. And that's the concentration. And that is in mole dm to the minus 3 of our ammonia molecules. Now we need to find the moles. So we're going to do moles is concentration times volume. So we're going to times that now by the volume. Of course, the volume in the question, we were told earlier, we've already used that, is 0.15 decimeters. And if we times these two bad boys together, we're going to get 3.25 times 10 to the minus 3, or 0.00325 moles. Boom. Let's move on. Right, what is this thing down there? Calculate the value at 74K for the equilibrium constant Kc for this dissociation of ammonia and give hydrogen and nitrogen. Oh, and state the units. Okay, well, we're going to need to do 1 over 0.118, and that's going to equal 8.47. And to calculate the units, well, if we look up here at this Casey expression, we've got mol per dm to the -3 over 4 lots of mol per dm -3. So if we cancel out, we're just left with 2 mol dm -3s. And what you do at the bottom, so we've just got mol dm -3 and mol dm. Oh God, that is the worst writing ever. And all you want to do there, I'm going to type because that just came out so bad. All you want to do there is combine the units. So we get mol 2 dm -6. So you just combine the units by adding them together, and there's your units. Okay, and here's our value, 8.47. So I might as well type that over here, 8.47. Nice. Right, moving on. 8. A student does 2 test tube reactions on 4 colorless solutions, A, B, C, and D. Table 4 shows the student's observations. So they've done 1 test on 4 different solutions and a second test on the 4 different solutions. Identify the gas formed in test 1. Describe a further test to confirm the identity of this gas. Well, we can see the gas was formed by 2 of the solutions, and that gas is going to be carbon dioxide. How do I know that? Well, we're adding a carbonate, and we can see here that the carbonate turned, the carbonate, and how would we identify that? We'd do the lime water test, turns cloudy as white precipitate formed. So at A level, you have to actually, rather than just goes cloudy, you have to explain it's a white precipitate. Okay, second question, 8.2. Explain how the observations from test 1 and test 2 can be used to show that solution B contains hydrochloric acid. So in this question, you have to use your highlighter, and you are only interested in these results here for solution B for test 1 and 2. So if we look at test 1, the effervescence tells us that carbon dioxide was released. So test 1, I can't spell effervescence, so I'm going to put E. Oh my gosh, I'm doing the capital thing again. Effervescence. Oh, that word is just gross. Effervescence shows CO2 released by H plus ions. So it shows that we've got hydrogen ions because they're releasing the carbon dioxide. It shows we've got hydrogen ions present because they're releasing the CO2 from the sodium carbonate. And then we've also got a white precipitate for test 2. So test 2, white precipitate with silver. Oh my gosh, silver chloride shows the presence of chloride ions. Okay, so this is going to tell me that chloride ions are present because we're doing the halide test for test 2. We're adding acidified silver nitrate, so nitric acid and silver nitrate. Nice. All right, let's move on. Moving on. All right, this is the final couple of bits before we go on to the multiple choice. Describe a series of tests the student can use to show that solution C contains ammonium sulfate. So some of you will have done this in triple science, and you'll know what is the test for ammonium ions. So test for NH4 plus ions, okay, you just want to, or warm with sodium hydroxide. So we're going to warm with sodium hydroxide. The sodium hydroxide reacts with the ammonium ions and releases ammonia, which turns, and you must say damp at A level, you can't skip that bit out, damp red, litmus paper blue. So that is going to get you your 2 marks that proves we have ammonium ions. Okay, now we next need to prove that sulfate ions are present. Hopefully you remember you had barium chloride. will form a white precipitate with sulfate ions. And you're going to get barium sulfate formed. And the white precipitate is the barium sulfate. So, uber duper. Now, the next bit of the question, the final bit, I believe, is 8.4. The student does an additional experiment to show that solution D contains a mixture of halide ions. So one of the halide ions is chloride. Add an excess of silver nitrate to 10 centimeters of solution D. Filter it off, wash and dry, and weigh it. Add an excess of dilute ammonia to the dried precipitate. Filter, wash, and dry, and weigh. Explain how the masses recorded during the experiment can be used to show solution D contains a mixture of halide ions. So solution D essentially has got chloride ions, probably bromide ions and iodide ions. We're just proving that fact. The fact is that when you filter and weigh it, we're going to say the mass recorded in step 2, or at first, the first mass recorded is larger than the mass recorded in step 4. So after you've kind of like mixed with excess dilute ammonia, the excess dilute ammonia dissolves the silver chloride. So the chloride ions get dissolved by the excess dilute ammonia, which means our mass of precipitate goes down. Now, the mass of precipitate should disappear altogether if it was just made of silver chloride. But the fact that it doesn't disappear altogether and we do get some mass left means that we've got silver bromide or silver iodide there, which won't dissolve in dilute ammonia. Of course, if you add concentrated ammonia, that's a different question. Okay, welcome to section B, the multiple choice. What you do here is you color your answer in next to the correct answer. So let's go. Which atom has 2 more protons and 2 more neutrons than chromium 52? We're really looking at chromium 52 here. So if you added 2 protons, we know the atomic number would change to 26. And if we added 2 protons and 2 neutrons, we know that that increases the nucleons, or the mass number will increase to 56. However, common mistake is people will then put the answer as B, chromium with 56 and 26. However, if you change the atomic number of an element, it becomes a new element, and that element would be iron. So the correct answer, the numbers do go to 56 and 26, but the elemental symbol will change because you've changed the atomic number. Okay, so the correct answer here is D. Right, let's look at question 10. An atom has all its electrons in the lowest energy levels. Which atom contains only 2 unpaired electrons? Well, if we look at helium, helium, it's got the 1s. And of course, if we draw the little box orbital, helium has only 2 electrons, and they're neatly paired together in the same orbital, the same 1s orbital. Beryllium, 1s2, so we've got the same situation that we have above with helium. And then, of course, we have 2s2, so the same situation again. It doesn't have any unpaired electrons in those orbitals. However, if we take oxygen, guys, we look at oxygen. Oxygen has, how many electrons has oxygen got? Well, oxygen has an atomic number of 8. And so it is 1s2, 2s2, 2p4. And if we look a little bit closer at this orbital over here, the 2p orbital, we can see that if you put 4 electrons in there, you're going to have, that is the worst drawing ever, but you can see roughly from this terrible drawing that I have 2 unpaired electrons in that 2p4. So the answer is C. Okay, moving on. Let's go. 11. The first 6 ionization energies in kilojoule per mole of an element are 1090, 2350, 4610, 6220, 37,800. So we go, whoa, that's what we want to look at when we've got a pattern in ionization energies. We've got a huge jump between the fourth and the fifth ionization energy. This one's nice and easy. We just go straight to carbon. We know it's in group 4. We know we're going to be breaking into a new shell. And so the answer here is going to be carbon there. There's a ton of energy when you're breaking into a new energy level. Okay. 12. In which pair is the first ionization energy of Y greater than that of X? So what we're looking at here is we're trying to compare Y to X. And we look at A and we say, if you were trying to steal an electron from A, you've got to break in to a full 2s orbital. If we look at Y here, you've got a lonely little electron in the 2p orbital. So that's going to have a lower ionization energy than X. So the answer is not A. Then if we look at B, B's got a 2p3, which is a half-filled orbital. But if we look at Y, Y's in a less stable position. It's got 4 electrons in the p orbital, 2 unpaired and 1 paired. So we've got spin pair repulsion on one of those, which is going to be easier to remove than these 3 electrons in this orbital that don't have spin pair repulsion going on. If we look at C, 1s2, 2s2, 2p5, and then we look at Y here, we got 2p6. Definitely it's going to be harder to remove an electron, regardless of the spin pair repulsion. A full orbital there, all those orbitals, the p orbitals there are full. It's going to be a lot easier than here, where the subshell is not completely filled and is missing an electron. So actually, our answer is going to be C. That is the position where Y is going to have a higher first ionization energy than C. Yeah, whatever I'm talking about. You get the idea, hopefully. Which statement about isotopes of an element is not correct? So this is key. A lot of people mess up the multiple choice and stuff like this. So you definitely want to be highlighting things. We're looking for the answer that's not correct. So they've got the same chemical properties, isotopes of an element. Yeah, there's no reason why they wouldn't. They have the same electrons in the outer shell. So A is a correct statement and not our answer. They have the same number of electrons in ions of the same charge. Yeah, that's going to be true as well. They have the same number of neutrons. Hopefully you all know this is GCSE. Isotopes have a different number of neutrons and the same number of protons, so they don't have the same number of neutrons. That is the incorrect answer. Okay, let's move on. Clearing the screen. Let's go. 5 grams of an oxide contains 4 grams of molybdenum. Oh gosh, I'm rubbish at pronouncing these difficult things. Molybdenum. What is the empirical formula of this oxide? Let's get down to the maths. So we know we have 4 grams of this molybdenum, whatever it's called. So I'm going to do 4G over its AR. And when I look in the periodic table, the AR of this is basically 96. It's 95.9. I'm just going to call it 96. Okay. And we work out the moles of this molecule. So where's my calculator? 4 divided by 96. And if you tap that into your calculator, you're going to get like 0.042, roughly. Now, how much oxygen have we got? An obvious mistake here is some people are going to put 5 grams of oxygen, but it said 5 grams of an oxide has 4 grams of molybdenum. That means we've got 1 gram of oxygen. So we're going to do, there's only 1 gram left in that oxide. That must be the oxygen. So we're going to do 1 over 16. And we're going to find out that if I divide 1 by 16, we're going to get an answer of 0.0, whoopsie, 625. Now we can see which one's bigger. There's more oxygen, 0.06 is bigger than 0.04. So we divide both by the smallest because we're doing empirical formula. Divide both by the smallest and hope we get whole numbers is what we normally do here. 0.0 4, 2. Oh my gosh, that's horrendous. Ruining the next question. Never mind. So that's going to equal 1. This is going to equal roughly 1.5. So I need to turn these into whole numbers. So I need to make these into whole numbers. What I do to one, I got to do to the other. So I times this by 2 to make 2 MO. And I'm going to times the oxygen by 2 as well. And that gives me my whole number of 3. So the answer is actually going to be C. Okay, that was a disgusting little moment I had there, and my working out's looking pretty rough. Okay, the equation for a reaction is ASH3 plus H plus, so plus a hydrogen ion. And then we get AsH4 plus. Now the AS, I think, stands for arsenic, which is in group 5. It's bonded to 3 hydrogens, so we can tell that 3 of those 5 electrons around arsenic are in a bond, and it has a lone pair. What type of interaction forms in this reaction? So you've got a hydrogen ion here, which has none of its own electrons. Remember, a hydrogen ion has no electrons. It's just a proton. So we're going to form a coordinate bond. The very first answer here, as that hydrogen ion must borrow the lone pair of AS. So just to show you what that would look like, AS is in group 5. 3 of those outer electrons around AS are here. It has 2 electrons hanging out here, and they're the ones that the H plus ion can come along and form a dative covalent bond or a coordinate bond with. Coolio. Let's move on. Oh, let's put a little tick there as well. Right, what is the correct trend down group 7 from fluorine to iodine? So does the boiling point of the element decrease? Well, you know that fluorine's a gas. Hopefully you know that iodine is a solid, a grey-black solid. So iodine is definitely, the boiling points definitely don't decrease, they increase. So that one is incorrect. The oxidizing ability of the element decreases. Obviously, if you look at fluorine, it's a lot smaller than iodine. And so with fluorine, that outer electron, remember they're in group 7, they have 7 electrons. That outer electron that it's tearing off, it's causing something else to be oxidized. So as you go down the group, the that is definitely correct. Because if you look at iodine, which is bigger than fluorine, it's a bigger molecule. It's going to be harder for it to steal that electron than with fluorine. So yes, the oxidizing ability of the elements do decrease down the group. That is definitely true. So I'm just working this out as we go, guys. So a little bit of a delay while my brain kicks into gear sometimes. Cool. Okay, but hopefully you're seeing how to think through the problems. Which of these ions, which is impossible to see now that I've scribbled my working out all over here, which of these ions has the largest ionic radius? Okay, so what you're really looking at here, positive ions have lost electrons, and they've got increasing nuclear charge. So really we're taking these babies out of the equation because that increasing nuclear charge and that loss of electrons is going to bring those electron shells closer to the nucleus as there's an overall nuclear charge on the ion. So we're really looking at between the chloride ion and the sulfide ion. And of course, which one's bigger, which one's bigger? And well, you can look at the atomic number. Sulfur is going to be bigger. Sulfur's atomic number is 32, whereas chlorine's is 17. So this is going to have a bigger ionic radius. Those outer electrons are shielded more from the nucleus. It's going to be bigger. So the sulfide ion. Plus, it's stolen 2 electrons as well, but they don't necessarily help the case. Which statement is correct? Chloride ions reduce concentrated sulfuric acid to form sulfur dioxide. Bromide ions reduce concentrated sulfuric acid to form sulfur. Bromide ions reduce iodine to form iodide ions, or iodide ions reduce chlorine to form chloride ions. What you've got to do with these ones is work out which is the best reducing agent. Now, over here on this question, we just discussed what happens to the oxidizing ability. We know that the ability to oxidize something, the ability to steal electrons decreases down the group. But the reducing ability of the halide ions actually increases down the group. So we're going to say iodide because iodide ions are bigger than chloride ions. It's easier for them to chuck away an electron to the chlorine. So we're going for iodide ions reduce chlorine to form chloride ions. And that's absolutely true. And it's because as you get bigger going down the group, those electrons in the iodide ion are further from the nucleus than they would be in the chlorine. And the chlorine is going to attract the electron. And yeah, there we go. Next question. You can't even read that. In which of these substances is oxygen in the highest oxidation state? So, little trick here with oxygen. Oxygen, do you know the oxidation state of oxygen? You should do by now. Oxygen is always -2. There's one situation in chemistry where oxygen isn't -2. Well, there's a few situations where it's not -2, but there's one situation where oxygen comes up against a more electronegative element and is therefore oxygen is positive and so has its highest oxidation state. And that is going to be when it is with fluorine, the only element more electronegative than oxygen. So the answer is going to be A. And in that situation, OF2, we know that fluorine is -1 and there's two of them, so a total charge of -2. And that means that our oxygen has a +2 oxidation state in that molecule. Okay, let's move on. Clearing, clearing, clearing. Which block in the periodic table contains samarium? And you can look at your periodic table and find that samarium is in the F block of the periodic table. Well, chlorine is an acidic gas, so I can see one that stands out to me straight away. So what is not a product? It's an acidic gas, so it's not going to release hydroxide ions. It's not going to cause hydroxide ions to be produced, because that would mean when chlorine reacts with water, it makes it alkaline and increases its pH. And that's not the case because chlorine is an acidic gas. So all of these others are things that can be created by the addition of chlorine to water. Which statement is correct? Magnesium reacts with steam to give magnesium oxide as one of the products. Magnesium acts as an oxidizing agent in the extraction of titanium. Well, magnesium plus titanium chloride, no. When you're in extraction, we're normally doing reduction, and that's absolutely right. So it's going to be a reducing agent. So no, it's not an oxidizing agent in that situation. Magnesium is going to be oxidized itself, but therefore it's going to act as a reducing agent. So that one is definitely wrong. Magnesium has a lower melting point than sodium. No, the group 1 metals have got a very low melting point. And if you think of the charge on sodium, it's +1 charge. So you've got Na with a +1 charge, and magnesium, of course, has a 2+ charge. So we know that magnesium has stronger metallic bonds, so it's going to have a higher melting point than sodium. So that's also wrong. Magnesium hydroxide is very soluble. No, it's sparingly soluble. Magnesium hydroxide is not very soluble in water. So our answer is this one. I could have really just got to that straight away, but there we go. All right, last question. Which is not responsible for conducting electricity? The sodium ions in molten sodium chloride, the electrons between layers of carbon atoms in graphite, the bonding electrons in a metal. This one might confuse you. What electrons are involved in bonding? Well, the ones that do metallic bonds are the delocalized electrons, or sea of electrons. So do they have something to do with conducting electricity? You bet your beep they do. So yeah, the lone pair of electrons in liquid water molecules. So there is lone pair of electrons, or there are lone pairs of electrons in water, but water is actually a simple covalent molecule, and pure water doesn't, or is a very poor conductor of electricity, as it doesn't have free ions or delocalized electrons with the ability to carry charge through the structure. So that might seem unusual to you, but water is not a good conductor. So why do people get electrocuted with the water on Earth? Because it's not pure H2O. It contains dissolved ionic compounds. So that's what makes the water on Earth in our taps and in the sea a good conductor of electricity, is the dissolved ionic compounds within the water. The water itself is a simple covalent substance and not a good conductor of electricity. And that's all I've got, guys. That's the end of the paper. Thanks for watching. I hope this helped you. If it did, leave a comment. Bye.